Hello everyone, welcome to the Easy Power Tuesday Refresher Series. My name is Jim Chastain. I'm an applications engineer here at Easy Power. And today we will do the wrap-up session, or part 4, on our series Introduction to Protective Device Coordination. And today we're focusing on relays and grounds. So welcome to all. Thank you for attending today. As we are in the habit of doing, we'd like to start with a couple poll questions. So if you would please respond accordingly. Let's make sure we get them on the screen here. Okay, so the first question is, how often do your projects include neutral grounding or high resistance grounding on the transformer? No obligation, just trying to get a perspective on the audience's involvement with some of these topics. We will be talking about ground coordination later in the session, but the primary focus, most of the focus, is going to be on transformer protection and coordinating relays. So let's give this another 5 seconds. We have about 50% participation. We do appreciate your attending today and being interested in the topic. All right, so here's how people have weighed in. Looks like we have a pretty good distribution of experience. Hopefully that will be expanded today, at least understanding. And so our next question is, how often do your projects involve an arc flash sensing relay? This is one of the technologies that we'll be exploring later in the hour. It's more of a recent technology in that it usually includes light sensing devices and fiber optic circles, fiber optic collection loops. And so it may not be something that's necessarily available in older systems. Okay, so let's see how we've responded here. So about the spread, I'd expect with experience being probably in the 50% range. Okay, so the agenda for today is to basically talk about relays and the TCC curves for relays, how to adjust them, and then specifically dig into a deep dive, if you will, in transformer protection, and then talk about other loads, and then finally coordinating ground systems in addition to coordinating relays with breakers. Now, we've described what coordination is frequently, and by all means, whenever you have a question, go ahead and throw it on the question block. We'll try to keep track of those real time. The goal of coordination is not a requirement for any part of the system legally, except for emergency and critical mission systems. And it's advised, though, to increase the reliability and dependability of the system by being able to allow the protective devices to trip as close to the fault as possible. So that means with motor loads, we're going to start coordinating with the last breaker or fuse being adjusted specifically for protection of the particular load. And then we have to slow down, if you will, or set upstream devices sequentially slower. And so in the overall scheme of things, the top relay, which will be the last protective device in the series, has to be slowed way down to be coordinated. Now, in the course of protecting transformers, and particularly the main transformer, you start by setting the relay to protect it, because it often can be the most expensive part of your system. And then in the case of motor loads, you want to have instantaneous trip close to the load, and then virtually no instantaneous trips in any device above it until you get to the main relay, because there you can predict what the worst case fault current will be and adjust accordingly. We've referred to a couple standards, ANSI standards, that describe the damage curves and damage potential for different technologies of transformers. And again, these give us the guidance that we're going to be following today. So these are not rules that we're talking about. They're recommendations for procedures or guidelines to set up protection for each of these elements. So we reviewed most of this on Monday, but basically we're looking for through faults. If the transformer has an internal fault, there's nothing we can do about it. We have to decommission it. And so there are several types of relays that can be used to determine a through fault. And we're going to try to go through a couple of these. The gold standard for transformer protection and overall system protection pretty much is the differential relay. And so there's multiple variations. We're going to be showing the advantage of utilizing a differential relay for main transformer protection. But it's a different setup as far as simulating what the results are. Just a quick side note, the question has come up in the past, do we need to include the internal fuse in a transformer package or transformer system as far as arc flash calculations? And the answer is no, because the internal fuse is primarily for fire protection. It's not for arc flash, particularly downstream protection. So it's basically something that's part of the internal design, and is strictly to prevent worst-case mechanical failure of the transformer itself. Now, the key points to consider when we're talking about transformer protection, first we have to determine the maximum load current under normal operations, and that's a standard equation that should be in everybody's cheat sheet. Settings of the relay, we set primary protection 10% above that number on the primary side, with the upper setting being suggested by the NEC guidelines, and I'll show the chart here shortly, at some percentage based upon certain conditions or stipulations about the transformer itself, but a certain percentage above that full load current calculation. And these limits are actually built into Easy Power. One thing we want to make sure we're cognizant of is when we're adjusting primary protection, we want to make sure it's not sensitive to the inrush current when the transformer is first turned on, because it would cause nuisance stripping unnecessarily. Then the through fault curves have a damage region and a mechanical region, and that's what we're going to be aligning protective devices with, comparing them on the TCC curves. And then, as I mentioned, the only circuit above, or the only system above the motor circuit protectors that has an instantaneous trip would be the main primary relay, because we can determine what the worst case current will be. And we determine that and then set an instantaneous trip somewhere around 10% above that. So I referred to the NEC max table. This is in table 453A. And basically, for primary voltages under supervised or unsupervised conditions, the maximum setting, if we're using a breaker, is 600% under 6% impedance ratio or less. Greater than that would be 400% of the max current, full load current. And so this is a chart that we'll be referring to periodically as we go through this process. Now, there's several curve profiles that are available on any manufacturer's relay data sheet. And so this is something I copied from a website that recommends, basically for transformer protection, we want to use a very inverse curve. Now, this is, again, not set in stone. It's just a guideline or a starting point for doing your coordination setup. Something that is important is understanding the need to have overlapping zones. For instance, the first example we're going to do is going to set up the zone for main transformer protection. And once we've got that dialed in, then we want to have an overlapping region that includes the next level of protective devices and make sure they're coordinated with the downstream protection on the transformer. And then the subsequent feeders, likewise, are coordinated with the upstream, with the overlapping element, and that will ensure protection for the whole system. So one of the things that I'm going to try to emphasize is if you follow this policy and coordinate on the largest downstream load, then the rest of the loads or the rest of the feeders in that particular bus will be covered. And it's a question that comes up, and sometimes it's worth being able to prove that to yourself. So let's jump into Easy Power and see how we're doing on this. So in this case, we have an unsupervised transformer with 8% Z ratio, just under 30 MVA, calculating out the primary full load current, 150 amps. And then if we go by the chart from the NEC table, the upper boundary for setting primary protection is going to be 600 amps. And the recommendation then is to set, again, the limits that we just described, and then adjust the time delay to clear the knee in the curve and the Z curve. And then finally, because I keep talking about instantaneous settings, for the primary protection, we can determine what that maximum current is, and we're going to set the instantaneous set point slightly above that, so we have protection and are confident that it's going to be adequate to the system requirements. Okay, so let's jump into Easy Power and talk about this. Okay, so, and just a side note, this file that I'm using is, for anyone that has the tools, is in the sample folder. This is Protection 1, and it's worth playing with these if you want to check up on what I'm doing. Okay, so what we're talking about is this system here. I'm going to selectively pick out primary overcurrent relay, its CT, the breaker, the transformer, the downstream overcurrent relay, its breaker, and then plot the TCC curves. By going to coordination, plotting the curve, we see something that looks like this. Now for grins, I'm going to turn off that. Well, first of all, I don't see any color on this TCC curve. I'm going to go to right-click, TCC options, and I want on my one line to sync the TCC colors to the TCC plots. So once we do that, we see kind of a rust color on this downstream secondary relay. And so that's this curve right here. So let's delete that just to not confuse the situation. Next, I want to talk about the transformer. So this looks a little bit different from what the transformers we started up talking about on week 1. If I open up the dialog box, under the TCC tab for the two-winding transformer data dialog box, I see 4 default check marks. So let's talk briefly about what each of these are about. So if I apply, it takes away my TCC curve. First of all, we're going to plot the 100% damage curve. This is the maximum that any fault needs to be able to protect against. So that gives us this dotted straight line. This is the worst case, 100%. You want to not exceed this curve, either at the time current plot up and to the right at any point in the life of the transformer. Secondly, let's invoke our frequent fault curve by checking that third box and applying it. Now we know that the upper part of the curve is thermal damage, and the lower part of the curve is mechanical damage from the magnetic impulse. And so this is a frequent fault plot line that's described in the ANSI standard, and given specific transformer conditions or parameters, the transformer will survive a limited number of excursions through this area, through this plot at this portion of the curve. So to be conservative, we want to coordinate against that and make sure, when at all possible, we avoid exceeding that guideline. Now, the thing that puzzles me is normally we see two plots on a transformer plot, and that's because for a single line to ground on a delta Y transformer, we plot a derating curve, and it looks something, it's a solid curve and it's offset by 58%. But if you'll notice, this overwrote that curve that we had. So the question is, why don't we have a separated curve? Why don't we have two curves? So I got a poll question here. Let's kind of jump into this. Question is, does a TCC curve have only one plot in this display? And if you were taking notes during the first week, we covered this. And I want to see if people kind of pick up on what I'm going for. So just, if you don't know, take a shot at it, because it's a learning opportunity. Okay, so we got about half the victims guessing here. This is good. And let's go ahead and show the results. We only have about 50% participation. No one's going to hold you accountable. So the reason there's only one curve is because this is not a hard grounded transformer. This has got a high resistance ground connection, and it's set up when we do the impedance setting for this transformer. So let's go back and talk about that. And what it amounts to, if I look at the transformer dialog box and at the impedance curve, we've got a 400 amp resistor set up in the neutral leg. So that means the maximum current that the system will see is 400 amps through that ground connection. Well, 400 amps is going to be somewhere down here in the mud, and so it's never going to be in this approximation of the phase current, which can be in tens of thousands of amps. So it's something that's handled separately, and the reason for the way the plot is set up is that because of the limited current, it doesn't really pertain to coordination. I mean, we will coordinate it, but it doesn't pertain to the max setting on the transformer impedance. Okay, that was a digression. All right, so let's come to the setup for R18. Now again, we know the full load current was 150 amps, so let's see where that is. When we plot the TCC curve for the transformer, we get the full load current calculated for us in this tick mark up here. If I hovered over it, I want to watch down here on the bottom information bar of the screen, and when I hover over that TCC plot, it tells me the max current is 1255 amps. Wait a minute, Jim, I thought you said the max current was 150 amps. Navin's asking a question. What's the determining factor for transformer good fault design current? So, Navin, I hate to bail on you, but this is I'm not really emphasizing the design of the system. I'm emphasizing the analysis and verification of the simulation and the ability to set protective devices based upon the data that's provided. So we can take that offline if you don't mind. So back to the question. Why is it display 1272 amps when we said the fault current was 150? Well, the reason is we're plotting this basis for this plot on 13.8 volt current. If we come back here and base the calculations on the TCC as the reference point, we get the same perspective, except now in the 115 kV range. And if we hover over this plot for the full load current, we see in fact it is 151 amps. Everybody see that? Now, according to the NEC setting, we want to be 10% above that. So this green tick mark corresponds to the pickup point for the setting on R18. And if we hover it over it, we see that we have a tap ratio of 5 to 200 amps max. If we left click and drag, we can see it changes the shape of the curve for the relay pickup, and 15% or 10% above 150 is going to be about 165. Looks like I have a 200 amp choice and a 160 amp choice. You see where I'm reading this in the insert of the dial. Now the same adjustment will be made in the setup for the relay itself. First of all, we're plotting the TCC curves. We're showing the momentary current tick mark. If we go to settings for overcurrent pickup, we have it set at 5, which gives us this 200 amp pickup. Using 4 isn't going to give us enough bandwidth, so let's leave it at 5. Now we've selected the very inverse curve, and we've picked out some number in the medium range on the TCC plot. So let's just do 2.8. Now we do have an instantaneous setting. Let's kind of go back and talk about that for a second. If I come down here and fault this bus, this is the worst case fault that this transformer will ever see in normal conditions. In other words, we have a hard fault in the secondary of the transformer. If we're looking at current, and when we fault this particular bus, we see just over 1116 amps will be the worst current that this system will see. So we can set our instantaneous plot slightly above this. And so 1116 amps, we're going to go for something near 1200. We go back to settings, instantaneous. So we can adjust that with a little bit more granularity if we want. If we just set it for 31 on the dial setting, it gives us 1240. Let's call that good. And so we see that we have pretty good coordination, pretty good protection here for the transformer. Now, I said we could set this as high as 400%, which would give us 600 amps. If we left click and drag that tick mark up to 480 amps, we can see we're already exceeding the frequent fault curve. So that doesn't make sense to take the maximum setting allowed. We're trying to do this on a conservative basis. So I'm going to leave this at a pickup of 240, which gives me plenty of guidelines. Now, another point to be made is that this should be the slowest device in the system. So we want to coordinate everything downhill from that. All right, so that gives me a pretty good starting place for R18. Let's put R4 back in the mix. Open the dialog box. Now, when I deleted it off the TCC curve, the effect was to uncheck this box for the TCC plot. So let's check the box again. Now, the TCC recommendations for full load current on the secondary side is 1250. So let's look at where we have this set. So pickup is at 1315. According to the NEC chart, we could go as high as 3140, 3124. So let's plot it and see how that looks. All right, so what we're talking about is the dial setting for this upper end. And if we reduce it to the minimum, which was 1252, let's say 5.0. So that's pretty close to the minimum. And you can see that it's not a bad starting place, but it's slower than the primary set point. So let's kind of go back here. And one other point. So here's our various inverse curve, and we're not turning on the instantaneous. So let's kind of come back here and set this a little bit higher, and then adjust the neon or adjust this. Now there's some granularity issues trying to move this with the mouse. So let's come back here and set it with the dialog. Okay, so we don't need it minimum. All right, so that gives us some coordination. Now, what's the significance of setting this any slower? Well, the significance would be it reduces a downstream arc flash. And so if we set this at, say, 8.4, again, slows down the device, but it doesn't give us coordination with the primary side. So let's go back to where we were. Now, as I kind of alluded to, once we set up our zones, we may have to come back and revisit some of these dial settings. But what we're starting with is a good starting point, and it will give us some reference to the downstream devices. So I'm not quite happy with that. And again, these aren't hard and fast, and they will vary based upon your particular system. Now, one other point to be made is that what we're doing when we're plotting relays, we're plotting the response time of the relay itself. We're not showing the clearing time because that involves the opening time of the breaker, which will vary based upon which breaker we're using. The tool will give us the ability to see what the maximum separation is between these two curves. If I select both, hold down Control and select both, and use the difference calculator, it will show us the minimum amount of time that these are separated, and at whatever current the difference will be, right? And so between a 5 cycle and an 8 cycle, this is an order of magnitude greater as far as the separation. So there's plenty of time for the one breaker to clear before the next relay is picked up. Okay, so let's say I'm going to live with this. So we talked about the curves, the instantaneous trip, the type of curve. We didn't talk about the instantaneous trip. Okay, when I go back to my transformer, my primary settings, if I fault all the buses, I see that there is an instantaneous trip on R18, and it's set for somewhere around 1220 amps, which is just slightly above this 800 or 1100 max fault current. If I want to see it, to see the, I'm going to fault that downstream bus. And because this now is, the set point is lower than this max extreme, I can display it on the single bus fault. And again, I'm showing that I'm clearing my inrush by plenty of margin. And I do have an instantaneous set on an upstream device, which will protect me from that 1100 amp fault. It looks like we're set for 1172. Okay, so let's say I'm happy with this. So we've done all of this. We talked about Tishmar. Yes, we're good. Okay, so next we want to look at the other end of the drawing, which is a transformer feeding a motor. And so again, the upstream protection is going to be for the transformer protection itself. The downstream, if there is well, we can see it here, the downstream breaker will be protecting the motor itself, and then any cables that may be sensitive to the max current. So we want to coordinate the breakers first, and the last one having an instantaneous strip, and then verify that the upstream relays coordinate. And so this is main switchgear down to 250 horsepower motor M2. So I'm going to save, I would save this plot, which I'm not going to do now, but the dial settings are saved. Now we're going to coordinate this leg right here. So again, we haven't overlapped between those settings and these top three breakers, but something I would do next. And for now, let's talk about this particular leg because we're going to start at the motor. All right. All right. The motor is the violet curve. First upstream device. Gotta set our first upstream device is BL3. BL3, it looks like it clears the asymmetric tail. I'm going to jog it just a bit to see if we can get a little better granularity. And there's a little bit of a concern about this being too close to the motor starting curve. I might adjust that, but we're well inside the thermal damage curve. Now, this breaker can be snugged up a little bit to our so what I'm doing is I'm hovering over the curve and then adjusting it based upon its reference to the downstream device. And if in some cases the size of the label box gets in the way. So we're going to move the magenta breaker over a little bit. See if we can get some coordination there. So it looks like I have good coordination between BL3 and BL1. So now the only issue is the relay protecting the transformer. So same setup here. Let's go ahead and take these two off. Leave them where they are. So delete that. Delete that. My worst case current, if I fault this bus, is 651 amps. And if I make that in reference to the 13.8 range, here's my max fault current of 58.4 amps. Here's my transformer pickup set at 75 amps, which seems like a reasonable place to be. I'm not protecting it well enough on my frequent fault curve, so I probably want to come down a little bit on my knee. So that's a good first order approximation. I'm going to turn these back on. So again, the same principles exist, starting at the bottom and then coordinate on your way up. And which one is this? So there's our upstream breaker. We have some coordination issues between it and the secondary of the primary of the transformer relay. So that might take a little work. Again, pulling it around on the screen gives me a limited amount of granularity. I might be better off doing this. Now, one thing that I didn't mention as we went through this, I'm on set point 1. There's an instantaneous setting with this this relay. And so, Jim, I thought you said shouldn't be an instantaneous setting except at the very first device. Okay, so I'm going to set my dial slower. I'll talk about the instantaneous in just a moment. Okay, so yeah, the instantaneous is set up on this relay, and the reason it doesn't show up is that the set point is above the max current that we'll see for a downstream fault. If I click in an open area and fault all the buses, I can see my instantaneous is set a greater than BL1 will ever see, and BL3. So there's no coordination issues even though I have an instantaneous element set. Fair enough? So whereas if I get a fault downstream, it won't even show up on my curve. Now, one thing I haven't talked about, and I'm going to use it now, is the advantage of smart PDC. And that is it's not the recommendation to kind of completely do the coordination, but it is a good sanity check to either start with a ballpark recommendation or see if there's anything I missed during my coordination attempts. So we're going to make reference to here and see what Smart PDC has to say about it. Any questions about what we've done so far? So we have coordination. We have some miscoordination on the relay. And it's telling me that it didn't like the downstream route. And so it pretty much ended up with what I did without recommendation on coordination here. So in this case, I think I'm a little bit better off not following PDC, the smart PDC, because I like having the protection against the overload relay. The motor coordinated with the motor. Okay, so the motor is the violet curve, and the first upstream breaker is BL3, and it's close to being coordinated. I have some risk of an overlap here. Some of that is due to the locked rotor current that we've set up. Some of it is due to the granularity of the breaker curve itself. So let's say we've gotten beyond this point. The next thing I want to show or prove is once I've got this coordinated with the largest downstream motor, in this case 250 horsepower, will it work or will it coordinate with all the rest of the devices on the feeder, on the main bus? So let me close this. Normally I plot to save the plots. And so the question is it going to coordinate? Will these upstream devices coordinate with this motor, which is smaller? So I'm going to start over here, pick out this breaker, this transformer, this relay, and the motor. Suffering from my data boxes being too big. Let's try it again. So this is a question that has come up before, and that is, how do we know that it's going to coordinate with the other devices? So again, I'm going to start back with this original plot. Okay, and basically we've slowed down the upstream relay and the upstream main breaker. And we're going to put that same plot overlay it with the smaller motor. So let's not save that. Let's go ahead and add this junk over here. And the question is this going to be coordinated? Now just to clear up the matter, let's go ahead and take off the larger load. This is just FYI. Take off the larger load and this 1 feeder breaker. Which will leave us with the motor control circuit on this motor, the motor plot, which we coordinated the MCP against, and then the main breaker and the main relay. So sure enough, this lower device, if it's properly coordinated with the motor, is going to be coordinated with the upstream devices. Now you might say, well, how come the MCP doesn't protect the motor from damage? The problem or the issue is we haven't plotted the overload. So we're showing an overload as part of the one line. We go in to set up the overload and plot it, properly picked manufacturer's part numbers. We do get the overload curve. There we go. Okay, so the overload curve is coordinated and it's within inside the damage curve for the smaller 100 horsepower motor. Does that make sense? So the motor control breaker is coordinated with the motor itself. So if we have a fault on the motor, let's do this. Fault the motor, then the breaker will protect the motor from existing in this part of the curve. Bomba, I think that's what you're asking. So let's go back. One more check that the tool has in it that can be very useful is what's called sequence of events. If I'm in coordination, pick out a downstream bus, fault a single bus looking at current, the motor will, the plot will show me, the one line will show me the current for that particular fault. It would also let me illuminate the sequence of events icon. And now instead of current, it's showing me the trip time. So if this bus faults, this breaker trips in 17 milliseconds, this breaker trips in 3 seconds, and the relay will trip in 3.8 seconds. So I do have coordination for a downstream fault. So hopefully that was beneficial. And so again, what we essentially did was coordinated this leg with this leg, prove that smaller loads on that same bus will be coordinated. And now as long as this breaker or this relay is coordinated with this relay, I've got coordination for my whole system, at least on that side. And so I invite you to prove to yourself that this will be the case. If you've got the largest load coordinated on a downstream bus, then your smaller loads will be coordinated. Okay, let's talk about neutral resistance grounding. A lot of designs, especially more so recently, are including high resistance grounding of the neutral leg. This is to limit the ground fault, which has several benefits, including increases personal safety, because you're going to fault on the first basic fault, ground fault that you have. It makes it easy to locate it. The disadvantage of a hard ground is that it can tolerate very high current before the system really will shut down. So the neutral resistance grounding does permit coordinated protective devices and it does allow you to continue to operate after the first ground based upon the fact that there's a limited amount of current. So before I get there, let's jump into Easy Power and see if we can see this. So basically, we've got two transformers that have resistance grounding. This is protected by, in this case, relay 16. So we're going to set up this 2. Let's go ahead and plot it with this 2. Plot the TCC curves and expand it a little bit. Now, the thing that's tricky is that normally you're looking at your phase overcurrent. We just want to look at the ground plot. So we need to apply a line to ground fault. And by doing that, now we see those curves set up for each of those devices. It's significant because R16 is set up with a 400 amp curve, 400 amp limit resistor, and we've scaled the curve to have a increasing fault or decreasing trip time with an increasing current. So the way it's set up with currently the setting is the higher the current. So this would survive a lower current for a longer amount of time. Likewise for R10, this is set up for a 200 amp. The transformer will show us. Well, I take that back. It's set up for a 200 amp ground current. So if we look at the relay, we want to make sure that the device function matches the function type, because this can be a little bit of an issue if you don't pick out the right selection. And then when we go to settings on trip 1, we have it set up for pick up at 100 amps and then have a decreasing or very inverse trip time according to the dial. And again, these can have instantaneous trip settings based upon the delay. Let's see if we can show it. So it makes a steeper curve, and we'd want to set it inside the limit. Yeah. So at the maximum 200 amp, it will give us an instantaneous trip on that part of the circuit. So again, that allows us to verify the downstream device was causing the current, the ground current that was being sensed upstream. So again, this is a policy or a judgment that you make based upon how much coordination you need to have between these systems on different buses and different transformers, and how important it is to have instantaneous protection somewhere downstream to keep it from affecting the upstream device. So the takeaway is make sure you're doing a single line to ground fault, and you're looking at the phase, the ground current, because if you look at both, it doesn't really make sense. Just because the phase current will have a much higher result. Okay, before I jump into that, I want to talk briefly on arc sense and differential relaying, which in this particular case, we have R17 set up as a differential relay primarily for the transformer. Now it's worth saying that we can include these downstream feeders if we had CT set up, adjusted the relay or set up the relay to consider what the nulling of the total current outflow from the switchgear is. So this can be a relay differential, a bus differential, or a ground differential. It can have multiple adjustments in the setting. So if we go back to how to do this in EC, the problem is, or the issue is, the relay can be sensitive on a very small differential between the upstream current and the total sum of the downstream current, and consequently be able to determine a fault much long before the full current is even hit the relay or the transformer. So that small differential in current, whatever it is that's been determined by the designer, will trip the device, and the device will then open the breaker long before it hits the maximum fault current that we've set up the overload relays for. Well, AZ Power can't simulate what that small differential is. So the way it's simulated as far as protection, when we go to set that bus up downstream, let's go ahead and see. When we have set this bus up for the downstream bus, under the arc flash hazard, instead of just looking at the calculated times, we say, well, we also want to look at the user-defined times. And this would be, I believe it was R17. The relay function would be 87, or the differential. And the time element includes the relay response time according to the data sheet, and then the opening time for whichever breaker the relay is tied to. And that summation, or that total, will give us the total response time that the manufacturer's data sheet will support. So whatever that total time is, we use in this column. Now this won't show up on the TCC curves, but when I do a fault bus in short circuit, I will get two responses or two calculations on my arc flash hazard report. One will be for R18 as overcurrent, and one will be for R17 as a differential. And the primary difference will be the response and clearing time, or arc time. So for overcurrent response, it's almost a second. For arc sensing or differential sensing, it can be 10 times better. And consequently, the instant energy would be reflected right here. So the instant energy is actually 10 times better. Okay, so that's differential and arc sensing relays have to be set up. Now, arc sensing is the same thing. We could have arc sensing for each of these downstream buses by putting the LCD loops, or the light sensor loops, in these areas, and then predicting what the downstream protection would be based upon the manufacturer's data sheet. Okay, it looks like we're running out of time. I did want to show this. I talked about sequence of events. It is useful to go in and show how a fuse protection will be displayed, and you're going to have conflict between multi-case circuit breakers, especially when you have panel protection for downstream loads. So that again is in the yes, that's in the protection one example, and it was something we've covered actually before. So I apologize for stomping all over this. It looks like we did a pretty good job of covering what we wanted. We went into detail of transformer protections with relays and fuses. Didn't touch that much on the fuses. We did coordinate basically most of the overcurrent protection devices, showing motor protection, high resistance grounding, and then differential relay simulation. Thank you for attending today. Thank you for supporting Easy Power. I look forward to having you join us down the road. Now, there was one question from Navin. The bus, you can control what's indicated on the bus. In that one example I was showing, just by saying, okay, well, in this case, I don't want to show if I want my differential relay to be the only thing that shows up for calculations, I'd have user-defined time. And then when I go to calculate this downstream bus, it will only show that. My instant energy will reflect that calculation. Thanks for the question. Look forward to talking to you down the road.